In our last lecture, we talked about several practical practice problems. So first, let me just quickly give you a quick overview. So we just did those simple setting, those random variables from standard normal, and these random variables from a normal with center mu, but still variance 1. Then we did a lot of probability calculations. So we are just left with two more problems, which are just practices for us to get familiarized with the relationships we have learned so far. So after this J's problem, which is about chi-square distribution, right? And related to that, we have the definition of the t distribution, which is defined as the ratio. The numerator is a standard normal random variable. The denominator would be a chi-square random variable divided by its degree of freedom, and then we take the square root. So then this is the definition of a t distribution, a random variable that follows t distribution. And the t distribution would have the same degrees of freedom as the chi-square degrees of freedom. That's the definition. So let's continue to our practice problem K. Okay. So for this, we'll say that use the t distribution. So in our traditional textbook, we have a table for t distribution. So we'll say this t table. So I would say it is regarding the CDF and quantile of t distribution with a degrees of freedom. So given the table, it will give you for a certain degrees of freedom, what quantile gives what left probability. So you will have that distribution in the table. And so given this table, we will use it to find the 80th percentile of this F distribution, F with numerator degrees of freedom as 1 and denominator degrees of freedom as 30. This is the problem. And to solve this problem, we will need to use that property we know for the t random variable. And then if we square it, then the squared random variable will follow F1, and the denominator degrees of freedom, the second degrees of freedom, will be equal to that t distribution's degrees of freedom. So we had that property last time. So basically, to answer this question, we will say that if we let a random variable, say t, I denote by capitalized T, follows a t distribution with 30 degrees of freedom, then we know that t squared would follow F distribution with 130 as its degrees of freedom. So this is a property we talked about last time. And I said that the t distribution is analogous to standard normal, while the F distribution is analogous to chi-square. Okay, so then we need to find this percentile, 80th percentile. So we need to find this constant C, okay, such that the probability that t squared is less or equal than C is equal to 0.8. This is what we define as the percentile. Given the left tail probability being 0.8, we want to find this corresponding value C, and that's what we define as the 80th percentile. So, but we don't have the CDF or distribution for the F distribution. We have to go to use the T distribution. Okay, that's the setup of this problem. So we know that since this probability, and also because t squared is non-negative, we know for sure that C is positive, okay? So since this is equal to, for t, is equal to the probability that t is between negative root C and positive root C, okay? And now we are going to use what we called the t-table to find this. And the key is that the t-distribution, as we said before, it is a symmetric distribution around 0. So let's say t is the zeros here. The t-distribution will have a bell-like shape, just like the standard normal distribution, but heavier tails. So here we want to find the c. So let's say this is the PDF of T30. We need to find, let's say root C is here and negative root C is here. So we need to find a C such that we will have 0.8 probability in the middle. That's what we need. And by symmetry, you should find that this is 0.1 and this is 0.1 in the left and right tails. Okay, so therefore, what can we tell from this is that since this is the equivalence between the two probability, so root C is the 90th percentile of T30. Then as long as we can use the t-table to find what the 90th percentile of T30 is, we are done. Okay, so similar to what we did last time, let's try to go to our R command so we can quickly see this. So now let me share this part. So using R, let's say that to find the quantile, we're going to use the QT function. In the QT function, the probability is 0.9. The degrees of freedom is 30. Okay, 1.31. That's our root C. Okay, so coming back to this visualizer. Let's see. Okay. Okay, so coming back here, then we can see that by looking up by the distribution, the CDF of this T30, we would have root C equals 1.31. That's what we just looked up. And then this can tell us that C is about 0.7161. Okay, so I just keep more digits over there. But this is just a strategy. So given the relationship, 1-to-1 relationship between a t-distribution with 30 degrees of freedom, we can derive a quantile for the F distribution with degrees of freedom 1 and 30 using this property. Okay, do we have questions? All right, so our last practice problem, let's call that L. The problem is that use the CDF of F2060, this F distribution, to find the probability that a random variable X larger than C is equal to, to find C greater than 0 such that this probability X greater than C is 0.99, where X follows F distribution with 60-20. Okay, so you can see by design, this problem is about the relationship between this F2060 and the other F60-20, their relationships. And this problem has a practical use in the old days when we used the table, because in the textbook, when it lists the CDF, including the quantile and left tail probabilities for F distributions, it only keep the F distributions where the first degrees of freedom is less than the second. It doesn't give the 60-20. It will only give you 20-60. And the primary reason is that it doesn't have to. because these two have an equivalence, so a one-to-one relationship. So as long as we have this table, we can look up anything about this distribution. So to answer this question, again, we are going to create a random variable that follows this F2060 and show that its inverse follows F6020. Okay, so I should say this. So given X follows F6020, then 1 over X, its inverse would follow F2060. Okay, and we only know the CDF of F2060, so we're going to use it. So P, the probability X greater than C, is equal to 1 over X less than 1 over C. Okay, and we need this to be 0.99. So what this tells us is that, so 1 over C is the 99th percentile of F2060. Okay, so then we just need to look up the distribution of F2060 so we can find 1 over C, and then we can find C. So the same idea. So now let's go back to R again. And we can see that if we just go here, so the percentile, 99th percentile of F can be found by this QF, and the probability we need here is 0.99. And DF1 is the first degrees of freedom is 20. DF2 is 60. Okay, the quantile we obtain is actually about 2.2, right? About 2.197, about 2.20. So let's come back to our notes, and we can see that. So by looking at the table, by the CDF of F2060, we have 1 over C about 2.20. Okay, and this will tell us that C is about 0.4545. So you just take the inverse of it. So this practice is about that important property that the inverse of an F distributed random variable is another F, follows another F distribution. You just need to swap the 2 degrees of freedom. That's it. Okay, so this concludes our introduction for all these distributions that was derived from normal distributions, including the chi-square distribution, T distribution, and F distribution. So for the R code, I'm going to post it so you can check it later. So it's basically the quantile function, and I can actually write it here if you need. So basically what I did is QF 0.99, DF1 equals 20, DF2 equals 60. That's it. That's the R code for this one. And for the previous one, the R code is just QT 0.9, and the DF is 30. That's it. Okay, so now let's move on to the, but I have to emphasize that our program is not a requirement for this class. I'm just using it more like a calculator, so we don't need to look up the table. That's it. Yeah, you are going to learn our program, I think, from Stats 20, and also in some other classes, you need to do the computation. But this class doesn't require programming or computation using R. But I just found it to be a very convenient calculator to use. Okay, so today we're going to move on to, sorry, I should wrap up what I said. So we talk about the derived distribution from normal distribution, including the chi-square, F distribution, and T distribution. So today we're going to introduce a whole new topic, which is called estimator. So I would say everything we have covered so far were basics of probability. And now we're going to move to statistics. So the difference between probability and statistics is that in statistics, we consider sampling. So we consider we have an actual random sample, which are some data, the data you call. While in probability, everything is hypothetical, everything is mathematical. So you can try to talk about properties of a random variables. While in statistics, we have the actual sampling, so we'll have actual data at hand. So this is the thing we call estimators. So, and we're going to talk about properties of estimators. So what do we mean by estimator? So to understand that, we need to know what is a parameter. And this is something I think Stats 10 should have covered somehow, right? The relation between a population with parameters and estimators based on a sample. So let's say that we have a population with parameter theta, okay? And from this population, we do this random sampling. We obtain, say, we denote by x1 to xn, okay? And this is our sample. This is called a random sample with size n. This is our random sample. And then we can construct an estimator from the random sample. So we'll say the estimator, let's call that denoted by theta hat. So we keep the notation theta to find the correspondence between estimator and parameter, which shows that this estimator estimates this parameter theta. And we put a hat so that we know this is an estimator, not a true parameter. So the estimator is a function of our random sample. So it is a function of x1 to xn. So for example, if theta is one-dimensional scalar valued, then this theta hat would also be scalar valued. So theta hat and theta will be of the same dimension, or more exactly, they should be in the same space. But it's a function that's just some, you can think about function as some operation on x1 to xn, so that you construct this estimator. Okay, so one thing I want to emphasize is that for the random sample and the estimator, they are both considered to be random. The reason is that from the same population, we can do random sampling for infinite number of times. And every sampling will give me different n values. So that's why x1 and xn are considered to be random. And so for different values of x1 to xn, I will get a different value for theta hat. So that's why theta hat is also random. So that's in our thought experiment. So we consider these to be, let's say in our case, IID random variables. Okay, this is what we consider. And so therefore, estimator is a random variable. So these are the things we don't get to observe for the whole distribution. But what we can observe is that given our actual data, so I would say our actual data is a realization of the random sample. So in other words, the n measurements we collected, let's denote them by small x1 to small xn. They are numbers, and each one is a realization of x1 to xn. So for example, this could be 0.1, this could be 1.2. So those numbers are the realizations of x1 to xn. So based on this random sample realization, we can have a realization of theta hat, okay? So this random variable theta hat, we can achieve a realization from our data, but we must be aware that this is not the whole picture, because there are other possible randoms, there are other possible realizations of this random sample that we don't get to observe. So therefore, there are other possible values of the theta hat we don't get to observe. And this whole way of thinking about this is what we call frequentist statistic. We consider that there is a fixed population with a parameter, and our data is just one realization of a random sample. So this is something we need to bear in mind when we think about estimators. So let me just give you, let's go back to R again. So let me say that here, let me share the whole screen. And now let's see this. So let's say that I'm interested in estimating the population mean. And here my population is just a standard normal distribution with mean 0. And I draw 100 observations from this normal. So my sample size here is 100. Okay, n is equal to 100. And each time I will get x1 to xn, one realization for each. And I compute the mean, our sample mean, as an estimator of the population mean. And I do this repeated sampling for 10 times. So then let's see, what do we get? Oops. Where did I go wrong? Mean function. Oh, sorry. Here. So if I run this, you can see that for the n times, each time the sample mean takes a different value. And no value is exactly equal to the population mean 0, right? And this is what we call statistical uncertainty, which means that the estimator realization you obtain from your actual data. So in reality, you only get to have one realization. So you only do the sampling for once. Then this is the sample mean you calculate, negative 0.0258. So given this, how would you infer what the population mean is? And here, because we are doing the simulation, we know the truth is 0. But in practice, you never get to know what the true parameter value is. Then how can you infer this 0 from this number 0.025? That's the question what we try to address. So therefore, you need to consider the uncertainty in your sample mean. And the uncertainty of your sample mean is exactly what we said, the formulation of sample mean as a random variable. So if you think about sample mean as a random variable, then you can derive its distribution. And given its distribution, then you can say, given the realization of negative 0.0258, how much or how far away is the true mean from it? Is the true mean more likely 0, or is the true mean more likely 1? So those kind of question can be answered. But if you don't know statistics, right? You just compute the sample mean and you stop here. You cannot say anything more beyond this number you observe. So that's mathematical statistics where it can start helping you, because we are going to tell you, given this number, what more can you say about the population mean? And the whole process I just said is called statistical inference. Okay, we're trying to do inference on the population mean based on our actual sample and the actual realization of the estimator. Okay, and to help you get a better understanding, let me try to repeat this by increasing the sample size. Now I'm going to increase the sample size to a very large number, let's say 10,000. Okay, and then let's see what happens. All right, these are the 10 realizations of the sample mean now. Did you see that they are now, each one is closer to the true mean 0? Yep, that's the effect of sample size. So basically it says that the larger the sample size, the smaller the variance of the sample mean as a random variable. So this sample mean is distributed around the true mean 0, but its variance decreases as the sample size increases. So therefore, you can say that with this larger sample size, you can do better inference about the population mean. So you can imagine that your inference will become more accurate, right? So I'm trying to give you the intuition before we do any math, but that's the drive of doing this whole mathematical statistics, to understand properties of estimators. Okay, so now let's come back. Let's move back to our mathematical discussion. All right, so we understand why we see an estimator is a random variable and why we only get one realization of it from our data. So now let's go into define something as a very important property. The property one is called a bias, okay? The bias of an estimator. How do we define it? It's actually defined as the difference between the expectation of the estimator and the true parameter. Okay, so one thing we need to be clear is that theta hat is a random variable, but once we take its expectation, then the expectation is not random. It's a fixed quantity. Just like if you have a random variable follows a normal distribution with mean mu, right? The random variable can take many, many values, but if you take the expectation of the random variable, its expectation just mu, and mu is not random. So this is no longer random, and theta as a population parameter is also not random. Okay, and this is what we define as a bias. So therefore, the bias of the theta hat is not random. It's a fixed number. So following the definition of bias, we can say that if the bias of theta hat is equal to 0, we would call theta hat an unbiased estimator. So this unbiased estimator definition is crucial. So you will see it a lot in statistical discussions. Okay, so what does unbiased mean? It means that even though for one particular realization of theta hat, it could be different from theta, and that's what we have seen. No sample mean is exactly equal to 0, the population mean. But if you repeat your sampling for infinite number of times, when you do that, you are going to observe all the realizations of theta hat. And then the expectation is basically, intuitively, is the average, I just write it here, the average of all possible realizations of theta hat. Okay, so you take all possible realizations to the average. This says that even though one realization could be different from theta, but if you take this average, then the average will be equal to theta. So what this says is that your estimator will have values that is around theta, but on average is equal to theta. So this is a nice property telling you that if you have the budget to do repeated sampling for many times, and then you take the average, then you will have a better estimator for theta. You know, they should be very similar. Okay, that's unbiasedness. So for this property, now let's try to do one important thing. This is an important result. So maybe I should call this a theorem, even though in my own notes, I didn't call this a theorem, but I think the importance is very high. So let's say that if we have x1 to xn, they are IID, okay? And they are from a distribution with mean, mu, okay, and variance, sigma square. So in this simple setting, then the statement is that our sample mean here, because we regard x1 to xn as a random sample mean x bar is an unbiased estimator of mu, okay? And that sample variance formula, Sn squared, we use this in our homework and also in our previous lectures, is an unbiased estimator of sigma squared. Okay, so the sample mean is an unbiased estimator of the population mean. Sample variance is an unbiased estimator of the population variance. So by the way we define their names, you would imagine that this should be the case, right? But recall that in our formula for Sn squared, that denominator is n minus 1 instead of n. And you may wonder why that's the case. And here's the reason. Using n minus 1 instead of n can make this Sn squared be an unbiased estimator. So we're going to show that. Okay, so to prove this, let's recall the definition of these two terms. So Xn bar is just the average. It's this. And Sn squared, by definition, is this. Okay, and then let's start calculating the expectation of each and see if this one has expectation equal to mu, this one has expectation equal to sigma squared. So the expectation of Xn bar, again, by the definition of expectation, we can exchange it from this addition, right? So we can move it into the addition. So this will be equal to, let me just write one more step. Move this into the addition will become the average of expectation of xi. Okay, and now by the condition, we already know for each xi, its distribution has been mu. So each exi is mu. So it's actually 1 over n. Okay, so you see the summation of mu for n times is basically n times mu. And that n times mu can be canceled. We can be dividing n will give me just a single copy of mu. That's it. So with this result, I can directly claim that Xn bar is unbiased, right, for mu. It's an unbiased estimator for estimating mu. Okay, and then next one, this. Okay, this is a little more complicated. The reason is that, yes, I can still do the same thing. I can move the expectation into the summation. But once I do that, okay, I'll just directly write it. Okay, I can do this. But once I do it, then inside each expectation, I now have two random variables, xi and xn bar, not just xi. I need to deal with that. And also xn bar, by definition, involves xi. Okay, so let's take a look at this term. But again, you know, because x1 to xn are IID, so one thing I know is that for each term here, it has the same expectation as other terms. So what I mean is that because of this x1 to xn IID property, okay, this property allows me to claim that the expectation of, say, x1 minus xn bar will be equal to the expectation of x2 minus xn bar up to equal to the expectation of xn minus xn bar. So these n terms in the sum, they're all equal because of the, and this is because x1 to xn, they're IID, and they're minus the same xn bar. All right, so because of this, I can say that I can simplify this sum. Okay, maybe I'll just go here. I can simplify this sum as just the sum of expectation of the first term, x1 minus xn bar square. Okay, it becomes the same term added for n times. So I will get it as n times this. So I can remove the sum. So I get n over n minus 1 expectation of x1 minus xn bar. Okay, do we have a question for this? Okay, sounds good. All right, so then what's left for us is to compute this expectation, right? Once we know this, we're done. So to compute this, the expectation of x1 minus, sorry, no bar here, minus xn bar square. And for this, let's try to open up this square. All right, so inside the expectation, I open the square. I will get x1 squared minus 2 times x1 xn bar plus xn bar square. That's it. Okay. So then what I'm left with is that I need to compute the expectation for each. Let's just put the expectation around each term first. So I will have expectation of x1 squared, okay, minus 2 expectation x1 xn bar. All right, and finally plus expectation of xn bar square. Okay, I will have those. So how do I simplify the terms? So the first one term, what I can do is pretty obvious, right? Given this. So the first term, what I'm going to do is to use the mean and the variance of x1. So I will say expectation of x1 squared, this is a formula we mentioned again and again, is equal to the square of expectation of x1, square of this, plus the variance of x1, right? We told you before that the variance is equal to expectation of square minus square of expectation. So now we're using this in the reverse way. And for this one, we know it's equal to mu square because its expectation is mu. And the variance, we know it's sigma square. So we know the first term. Okay, for the third term, we can use the same strategy. So since we can easily show that the expectation of xn bar, which we already did, is equal to mu, the mean stays unchanged, and the variance of xn bar. So this is something we did before, is actually equal to n 1 over n times the variance of x1 of each xi. And now I'm just using x1 as a representative. It's actually equal to sigma squared over n. Okay. Or maybe I can go one more step. Maybe for this one, probably this is why I skipped one step here. Okay. This is equal to 1 over n squared summation of variance xi. And then because xi's are IID, so I represent each one by variance x1. So I get n times variance x1. So that's why it's this. Okay, so given xn bars mean and variance, I would have, so expectation of xn bar squared, our third term here, I would do, it's equal to the square of xn bar plus the variance of xn bar. All right, and then I would get mu squared plus sigma squared over n. So I'm done with the third term. Now for the middle term, for that one, I need to worry about this x1 times xn bar because x1 is involved in xn bar. So since x1 times xn bar, now I'm going to write xn bar out, right? It's equal to x1 times this thing, x1 plus x2 plus 2xn over n. This is the definition of xn bar. So therefore, if I do this, you can see I'm only x1 in the sum is special because I have x1 appear twice. But everything else in the sum is not x1. So I separate them too. So I will get x1 squared over n plus, basically for the remaining terms, I can write it as just x1, x2 plus 2x1, xn. Okay, so I'm here. Now I will put the expectation around each term. So the expectation of x1, xn bar would be equal to 1 over m expectation of x1 squared. Okay, and for the remaining, it's actually, I put it out 1 over m, and I'm just doing summation of I from 2 to n, the expectation of x1, xi. I didn't do anything special. I just changed this notation to the sigma summation notation for simplicity. Okay, now let's try to go one more step, do the simplification. For the first term, we already had it, right? Expectation of x1 squared is sitting here. So I just copy it, mu squared plus sigma squared. And here, how many terms do I have inside? N minus 1 terms. And each term should have the same expectation, because for I being 2 or I being n, because x2 and xn are IID, so therefore I just have the same expectation. So for the second one, I can write it as 1 over n times n minus 1 copies from the sum times expectation x1, x2. So I just set I equals 2. Okay, so one more step. I copy this 1 over n mu squared plus sigma squared and plus n minus 1 over m. And this expectation, now I'm going to use the independence. So x1 and x2 are independent. Okay, they are independent IID. So therefore, I can write this as expectation of x1 times expectation of x2. All right, and each one is mu. So this is equal to mu squared. All right, so then finally, I'm there, right? So I just combine the terms. So 1 over n mu squared can be combined with this n minus 1 over n mu squared. So I get mu squared. And I have 1 over n sigma squared. That's for this cross expectation. So now I'm going to put this, let me call this number 1, and let me call this number 2, and let me call this number 3. Put 1, 2, 3 back into the above formula. Hence, the expectation of x1 minus xn bar squared from 1 is equal to mu squared plus sigma squared. The second one, I need to put minus 2 here. Minus 2 times mu squared plus 1 over n sigma squared. Finally, term 3 plus mu squared, okay, plus mu squared plus sigma squared over n. All right, what do I have? So you see this mu squared and the other mu squared will be canceled by this negative 2 mu squared. Okay, so mu squared is gone. For sigma squared, I have a 1 here. So basically I'll put, this is 1, and this one is minus 2 over n. Finally, plus 1 over n times sigma squared. All right, so what do I have? I have 1 minus 1 over n. 1 minus 1 over n is n minus 1 over n sigma squared. That's it. That's what I have. So now finally, you can see that this is just the expectation of x1 minus xn bar squared. And moving back to this expectation of Sn squared, you see what I have down here is n times n over 1 times this term, right? And now I just told you this term is equal to n minus 1 over n. So together, the expectation of Sn squared, so from the previous page, is is n over n minus 1. I just copy it. N over n minus 1 expectation of x1 minus xn bar squared. Okay, and based on what we just derived, n over n minus 1 times n minus 1 over n sigma squared. So I get sigma squared. And this result tells us that Sn squared is unbiased. It is an unbiased estimator for estimating sigma squared. That's it. So this whole derivation, I would say it's quite important, and I want everybody to be able to repeat what I just did. So I will say here the key thing is that there are two core components. One is that you need to be very familiar with how to handle expectation and how to handle expectation for independent random variables. These are all basics from probability. And the second core thing is that you need to do algebra, right? You need to manipulate the terms to combine the similar terms. So algebra, probability are the basic math foundation for this mathematical statistics. So I think this is one of the most important things that I hope everybody should be able to do out of this class, because knowing why we need the denominator here, the denominator as n minus 1 instead of n. The answer is that we want to make this estimator unbiased. And you can imagine if it's 1 over n here, it's just changing a constant, right? Then you know the result is that you're going to have a biased estimator. Because if you change to 1 over n, you're going to multiply this by n minus 1 and divide by n. Then you can see correspondingly, if you multiply this by n minus 1 divided by n, then the expectation will be also multiplied by n minus 1 divided by n. So you're going to have a biased estimator instead of unbiased. So let me just write this down. So if you have this estimator, 1 over n, this is your estimator instead of Sn squared, it's basically Sn squared multiplies by n minus 1 divided by n. That's how you can go from here to here. And then correspondingly, based on what we have, you are going to have the expectation of this, right? So then you will say that this is a biased estimator because the expectation is not equal to sigma squared. But again, you can see that if your sample size n is large enough, then the difference is negligible because this ratio n minus 1 over n is going to 1, right? So then the bias is going down to 0. So that's why this correction using n minus 1 is instead of n is only meaningful or is only important when you are dealing with small sample size data, like n less than 10, n less than 20. In that case, this difference could be quite noticeable. All right, so any questions about this derivation? We basically show that the sample mean is an unbiased estimator for population mean. Sample variance is an unbiased estimator for population variance. And in our whole derivation, we didn't talk about the distribution at all. We just said it's IID. So we just say that they're IID and they have this mean mu, population mean mu, population variance sigma square. We didn't say they are normally distributed or not because we don't need that. So this unbiased property applies to any distribution. Okay, so we just told you these two easy estimators, right? You can easily construct them from the sample. But how about for some complicated population parameters? How do we estimate them? How do we construct estimators? So for this, our next topic is about, we call this method of moments. Short as MOM, estimators. So this is what we will introduce as the first way of constructing estimators. It's very intuitive and it's very easy to implement. Are we done with properties of estimators? We just talked about the bias, but later we'll talk about its variance. But just for now, we finished the bias, but I'm going to introduce how do we construct estimators, right? The logic is that once you know what your estimators are, then it makes sense to talk about their properties. But for now, we just introduced sample mean and sample variance as two straightforward estimators we already had. But we're going to tell you how to construct estimators more generally. So basically, I'm talking about here how to find this f. How to find this f function so you can convert a random sample into an estimator. And this is the first way, which we call method of moments. Okay, so the logic here is that you are going to use sample moments as estimators of population moments. Population moments. Because population moments are also parameters of a population. So let me just define what do we mean by population moments. So basically, let me just write it here. So let's say that sample moments, I put it on the left, and population moments on the right. And for each moment, we need an order. So let's say we have the first moment at the population level. It's basically the expectation of a random variable. So let's say that, how about this? So we just give you this notation first. So let's say that we have x1 to xn. This is a random sample from a population. Random sample from a population. Okay, and we also denote that a random variable, an independent random variable that's independent of our random sample, is also from the same population. So this is just for our notation convenience. So when we talk about any moments about the population, we can use this hypothetical X random variable for representation. Well, x1, xn are just a sample of size n for which we can obtain realizations. So this is our sample. This is a random variable from the population. We'll try to distinguish those two. So then when we say the first population moment, we actually mean expectation of this x. So x follows this population, and you could imagine this population as a distribution, like a normal distribution, exponential distribution. Each one represents a population. And its expectation of this random variable that's from the population, we denote this by expectation of x. And that's what we call the first moment. And recall that we also often denote this by the notation mu. Okay, this is for convention. And second moment, correspondingly, is expectation of x squared. Okay, and let's say that if we go down to the kth moment, population moment, is expectation of x to the power k. These are the population moments. So like for normal distribution, we know the first population moment is mu, right? The second population moment is equal to mu squared plus sigma squared, which is just what we derived. So for the second population moment, this is not specific to normal distribution, but holds in general. It's equal to the square of the first moment plus the variance. If the variance is denoted by sigma squared, this is it. Then on the sample side, we are going to basically have the sample moments. So in the sample moments, we are going to replace expectation by average. So you can imagine that the sample just has n values. And you may imagine that these n values themselves form a distribution. Okay, so you have a distribution of n values. So from this, you can also define what's the first moment, what's the second moment. And in this sense, each value receives a probability 1 over n. And we also have a term for this distribution, we call this empirical distribution. It's the empirical distribution specified by your sample. From this, you can compute the moments. So then the first moment is basically the average of the x1 to xn. So the rationale is that you give each xi a probability of 1 over m. And then with that distribution, the expectation is simply the average of x1 to xn. And then second moment correspondingly is 1 over m xi squared. Okay, and then the kth moment is the average of xi to the power k. All right, so basically from this, we would just say that the method of moment is based on this relationship. So the MOM estimator of expectation of x population first moment is it's this. And if I make this more general, I can put k here and k here. So for any kth population moment, its MOM estimator is the corresponding sample moment. That serves the foundation. Okay, and then the question you may ask is, what if my parameter, the population parameter I want to estimate, is not one of the population moments, right? Then what would you do? So to answer that question, you are going to do this. So if theta is not a moment itself, but it can be expressed as a function of some moments. Actually, we can show that it's actually the case. So that's why the moments are so important. So once you specify all the non-infinity moments of a distribution, you specify the whole population. So in other words, given those moments, you know the distribution. And recall that we have the moment generating function. If you recall that for the moment generating function, we can expand the function using the Taylor expansion, right? Then the coefficients for t squared, for t cubic, those are just the moments. So then given those moments, you can actually specify the moment generating function by the Taylor expansion. So that gives you a sense why, given the moments, we know the distribution. But coming back here, so if we can specify the parameter we want to estimate as a function of some moments, okay? So let me just write it as, if I can write it as the function of, say, the first moment and the second moment. I'm just making an example. For example, okay, then the method of moment estimator, MOM estimator for theta, I denoted by theta hat with MOM in the subscript, is just the same G function applied to the corresponding sample moments, 1 over m sum xi and 1 over n sum xi squared. I from 1 to n, I from 1 to n. So you just replace the, sorry, it should be this curly braces. Yeah, you just replace your population moments by the corresponding sample moments. Apply the same G, and that will be the method of moment estimator for that theta parameter. Okay, this may look a little abstract, but I'm going to give you some concrete examples so we can see how this is applied. So the first example, let's do some examples. Let me see. The first example is that, let's say that we have x1 to xn IID from Poisson lambda. And the question is, find the lambda hat MOM. Find the method moment estimator of lambda. We didn't touch the unbiasedness yet. So there's no, we will talk about that. So I would just say for method moment estimator in general, it's not unbiased, but it's case by case. So we can actually say that for each sample moment, yes, you can say this. Each sample moment is an unbiased estimator for the population moment. There's no problem with that. But if you're talking about this case, right? So for this G function, and that's your parameter of interest, and this is your estimator. If you put expectation around this estimator, you need to worry about whether this expectation and G are exchangeable or not. That's the thing we need to consider. If G is a linear function, yes, you can move the expectation into the G, but not always. If just nonlinear, then that's not always. So that's why for the unbiasedness of method of moment estimators, it's case by case. Yeah, but you made a very good point, Brandon. So we can say that these things are unbiased. Each sample moment is an unbiased estimator for population moment by definition, and there's no problem for that. Okay, so now for this example, actually, we can say that because, so to answer this question, let's have that hypothetical random variable x, let it be Poisson, let it follow Poisson with parameter lambda, and we need the first population moment. So expectation of x is just lambda based on the property of Poisson distribution, right? Poisson lambda is indeed, or is just the first population moment. Then let's use the first sample moment to estimate it. So lambda hat MOM is just xm bar, right? Because this one, we also give a notation before xm bar. That's it. This is the simple case because the parameter of interest happens to be the first moment. All right, so that's just an easy start. Now let's move on to example 2. So in example 2, now let's say that we have x1 to xm. They are IID, Poisson, no, not Poisson, sorry. They are IID uniformly distributed on this interval 0 to theta. Okay, so with this setup, now the parameter of interest is theta. The question is find theta hat MOM. Okay, to answer this question, we are again going to derive the first moment and see how it is related to theta. So usually, if you have just one parameter to estimate, the first moment is probably enough, okay, if it can be expressed in terms of parameter. But sometimes you need to go to the second moment. So depending on the nature of the parameter. So now let's do let x follow this uniform 0 to theta distribution. Okay, so now this is something we need everybody to be able to compute, right? Given this uniform 0 to theta, what's the first moment? So we should have expectation. This one is something you can compute by intuition without even doing integration because it's uniformly distributed in this interval. So its expectation should be the middle, right? It should be just theta over 2. So with this, now you see the first moment has a relationship with the parameter of interest, right? So theta is basically 2 times the first moment. Now I'm going to find the method of moment estimator of theta by changing this first population moment by the first sample moment. So theta hat MOM will be equal to 2 times xm bar. Because xm bar is an MOM estimator for the population first moment. So that's it. So we're just implementing this principle I wrote here. If you have a G function that can define your parameter based on population moments, you just apply the G function to the corresponding sample moments to find the corresponding MOM estimator. Okay, this is the second example. Now let's move on to the third example. Now let the random sample x1 to xm be IID. Normal distribution would be mu, variance sigma square. Okay, and now we want you to find the two parameters method and moment estimators. So find mu hat MOM and sigma square hat MOM. So you're going to find those two. And again, we're going to use our population moments to get a start. So now let's let a random variable, hypothetical random variable, be from the normal distribution. So here we need to go to two moments, two orders. So then expectation of x is equal to mu, and expectation of x squared is equal to mu squared plus sigma squared, right? So this is what we know so far. So then you're going to express each parameter as a function of moments. All right, so I can write mu is there. It's just the first moment. And the variance, sigma squared, can be expressed by the two moments. Right? Second moment minus the square of the first moment. Now you're going to just replace the population moments by the sample moments to get the MOM estimators. So based on this, the mu hat MOM is just xm bar, right? The first sample moment, and sigma square hat MOM is just the average of the sample, is the second sample moment minus xm bar square, right? Okay, and since we just talked about the unbiasedness, then we can go one more step and see what's different. So if you go look at this sigma square MOM and expand it, I can tell you that. So with some algebra, we can show that the sigma square MOM, it is actually 1 over m xi minus xm bar square. Okay, why is that? This is something we probably have done before, but it's actually very straightforward. This is very important to connect this with this. The reason is that if I expand the square term, let's just do it. If I expand the square term, we would have xi squared minus 2 times xi times xm bar plus xm bar square. Okay, if I expand it, then you can see that I only need to keep the sum around the first two terms because they involve I. The third term has no I can get it out of the sum. So basically, I'm going to keep, okay, I'll just write this way. Summation xi squared, first term, minus 2, because xm bar doesn't involve I get it out of the sum, xm bar, summation xi. Okay, I become this. And finally, this one gets out of the sum, becomes n copies. All right. And then finally, you're going to use the fact that this thing, summation of xi, is just equal to n times xm bar. Okay, using this property, then you are going to show that in the bracket, I'm having just summation of xi squared minus there's a minus 2m, cancel with n, I have minus m. Okay, that's what I have. And then if you move it out, it's exactly the MOM. All right, so I'm just did this derivation for you, but the key is that I want to emphasize here the MO in the MOM estimator, you have the denominator as n instead of n minus 1. So in other words, what you can claim is that so sigma square hat MOM is a biased estimator of sigma squared. Right, and that actually answers Brandon's question. So the method of moment estimator is not always unbiased. Okay, because here the sigma square as a function of moments is actually not linear because you have a square term around the first moment. Okay, so that's example 3. Do we have questions? All right, if not, then we will do example 4. So in example 4, we have x1 to xn IID from a normal distribution again. But now I'm telling you that I know the mean, the population mean is 0. I just don't know the population variance, which I denote by sigma square. Okay, and then I want to find sigma square hat MOM. This is a very interesting problem because compared to the previous one, you know more. You know the population mean. And then in this case, how would your estimator for the population variance be different? In terms of the method and moment, actually there is difference. So we're going to use the true mean we know. So let's start again. Let's let a hypothetical random variable to follow this distribution. Okay, and then what we would have is that the expectation, the first moment is equal to 0, okay? And the second moment, which we know by definition, is the first moment square plus the variance. Now the first moment is 0, so we only get a variance, which is sigma square. All right. So because the parameter is just the second population moment, so its MOM estimator is just the second sample moment, and that's 1 over n. That's it. So you see, the difference is that here, this variance MOM estimator doesn't involve subtracting the sample mean. You don't do that. The reason is that the population mean is known to be 0. And you use that, you no longer use the sample mean as an estimator for the population mean. So this is a special thing about the method, the moment estimator. So in other words, even though you are interested in estimating the same parameter, sigma square, but depending on whether the other parameter, the mean parameter is known or not, the variance MOM estimator will change accordingly. Okay, so how to interpret this result? So basically, you see, compared to this formula, I'm using this. This can be interpreted just as in other words, you're not using x and bar, you're using 0 because you know 0 is the true mean and you want to use it. Okay, so finally, let's do a more challenging problem, a practice for MOM. So now let's say that x1 to xn, they are IID with PDF, probability density function as this. I denote this by fx equals to theta plus 1 times x to the power of theta. And for x, I have 0 between 0 and 1. So this is the range of values that each random variable can take, okay? And also for this theta, I have a constraint, so theta must be larger than greater than 1. And the question is to find theta hat MOM. So here, this parameter theta specifies the density function. And with this density function, we know how these IID random variables are distributed. So therefore, given our random sample, we want to estimate this key parameter theta that determines the distribution using the MOM method. So to answer this question, we again start with a hypothetical random variable that follows this F, right? That follows this F density. So now let's go to the first moment of this density of this distribution, then expectation of X. Based on the definition of expectation with this density, we should be able to do integration. So the range is from 0 to 1. So the integral goes from 0 to 1. It's X times Fx dx, okay? And now let's put in Fx. Okay, so this is a standard problem from calculus. We're just doing the integration for power function, right? So one more step. Theta plus 1 times x to the power theta plus 1 dx. All right, and then I can tell you it's basically theta plus 2 in the denominator, theta plus 1 from here, x to the power theta plus 2 from 0 to 1. I put in 1 and put in 0, and its answer is just theta plus 1 over theta plus 2. That's it. So in other words, the population first moment is a function of theta. So now I'm going to solve what is theta. How can theta be represented by the population first moment? And I can give you the answer. It's 2 times expectation of x minus 1 divided by 1 minus expectation of x. That's it. And then I put in the sample moment, first moment of sample, to replace the first population moment to get my method of moment estimator. So then finally, theta hat MOM will be equal to 2 times xm bar minus 1 over 1 minus xm bar. That's it. Okay, so these practices are just showing that as long as you can express a parameter as a function of population moments, you would immediately obtain the method of moment estimator for that parameter, because you can just replace population moments by the corresponding sample moments in the estimator construction. So this is a very straightforward approach. But next time on Wednesday, we're going to tell you a better approach in terms of estimator properties. That is called the maximum likelihood estimation. So it is known that the mathematical statistics theory told us that the maximum likelihood estimator is a better estimator based on properties we're going to define next. So please make sure that after this class, you fully understand what the method of moment approach is doing. So next time we're going to move on to our approach 2. Okay, so I'll see you on Wednesday. And will Wednesday's lecture be on the midterm? Okay. So maybe yes, maybe not, because I feel like given the after Wednesday you're going to have, so still you'll have until next Monday to review for the midterm. But I can say that, so we will not test you heavily on the new materials, right? Like MLE is probably going to be mentioned, but not the core of the midterm, because we have so much before it. And no, there will be no practice questions uploaded, because this is a new format. This is a new testing format. We're going to test you on multiple choice questions. So I would say the best practice will be your homeworks, you need to fully understand your homeworks, make sure that there are no gaps in your understanding, and also the lecture notes. So we will not test you anything beyond that, beyond what we have covered in the lectures and discussions and homeworks. Okay, so see you next Wednesday. Bye. Bye.
Thank you.
Thank you.